So, hello to everyone. My name is Meriton Ramizi. Since almost a year, I'm a PhD student at the Technical University of Vienna. Today, I would like to share with you the work we have done for my master thesis, which is about water permeable pavers. So the aim of this work was to optimize mix design which is suitable to produce water permeable pavers by adding a cement paste which is fluid enough to cover the surface of the grains and binds them together while not flowing during the manufacturing process. The main challenge was to maintain the connectivity of the voids and retaining sufficient water permeability and mechanical properties. Looking closer to at the cross section, we can clearly see the uniform distribution of the interparticle voids and the aggregate grains covered by a thin layer of cement matrix, which making it possible to achieve the desired mechanical properties according to the standards. In this sketch, I try to simplify the information what I just shared so far, and this sketch will follow us in coming slides. So here you can see shown a mixture of porous concrete, where you can see the aggregates covered by a thin layer of a cement paste. In German, feucht. I couldn't find it in English. Add means the earth. The idea or the meaning behind that is that it has which is mixed with a tiny small amount of water. So the is between 10 and 15%, and the water binder rate 28 to 0.40. With single size aggregate with no fine sand, lower solid volume fraction of the aggregate, providing a higher void content, therefore reducing the mechanical properties. Porous concrete, there is no big difference, just that porous concrete, as I mentioned, have small particles, as I already mentioned, decreasing the solid volume. And paste volume fraction for normal concrete is approximately 25%, and on the other side 10% lower, and on the other side it's 27%. So when we topic, we face three main challenges, which is the first one is how to optimize the cement paste and properties. Aggregate size and shapes plays an important role to the mechanical properties and water permeability. And the last one is manufacturing process, how to simulate the manufacturing process at the lab, how to make the samples in a real way. First thing we try to do to optimize the cement paste, we try to relate it with was not easy, and can say that we failed. With assuming that all particles have a spherical shape in order to calculate the volume. And then for the same grains, we took by the approximately 100 grains, took pictures and analyzed with imaging. And for the same grains, we measured the real volume with a pycnometer. So the difference was above 50%. And then we continued to investigate this quantity on volume and on mass. We know that the volume and the mass difference, so decided to relate it to the mass of the aggregate because it was easier to create or to make the Excel sheet model to calculate the mix proportion. So through today, the quantity of the cement paste is always based on the mass of the aggregate. In this picture, you can see the main part, how the concrete pavers are produced. They are pressed and compact. They are pressed and vibrated in the same time. You can see the mold here, which is filled by this sliding unit, which goes to the container, takes the required amount of the mixtures, fills the mold, and then the hydraulic press, the compactor goes down, compacts, and the vibration is happening in the same time. This process happens approximately for 5 seconds. The challenge here is how to avoid the flowing of cement paste during this vibration and compaction energy, which is quite high. Right after the pavers, the samples are demolded and sorted to the curing room. So this is what we did to simulate the real manufacturing process in the lab. Vibration plate, a steel mold. You can see the screws, which was practical to demold it right after the vibration and compaction process. And for the compactor, we used this concrete sample, which was approximately 6 kilos. So not the best simulation on to simulate the hydraulic pass, but the best what we could do. So here is shown a picture made in our lab with crushed aggregate 3 to 5 millimeters, where you can see the water flowing through the stone. And now I'm gonna go through the work which we did in our lab, which is completely based on experiments and on optimization. So for the binder, to investigate the fresh properties of cement paste, we have used cement, silica fume, superplasticizer, and tap water. In the diagram below, you can see the particle size distribution. The blue curve presents the cement, and the orange one, the silica fume. 4 different sizes of aggregate were used: river and crushed. River aggregate with the size 1 to 3, and crushed aggregate with the size 2 to 4 millimeters, 3 to 5, and 4 to 8. We have done several examinations on aggregates, such as water absorption, density, and packing, solid volume fraction. So to avoid the flowing of the cement paste during the vibration and compaction process, we have designed a cement paste with 0 slump, 0 spread. We have tried with Teresa to do some rheological measurement, but they were not possible because this paste has a high yield stress. The required amount of the ingredients were measured precisely according to the recipe and mixed approximately 30 seconds. And then right away, the mold was prepared for the compaction and vibration process. So here is the vibration and compaction process. As I said, right after the mixing, the mold was filled, compacted and vibrated for 30 seconds. Right after, demolded and sorted in a climate chamber for 24 hours. So to measure the water permeability, as you can see in a picture, this setup with impermeable wooden plate was constructed. The sample was placed on the setup and sealed with silicone. And then the setup was inserted in 1 meter long pipe. The pipe was filled with water, and the time for the water needed to pass through the sample was measured to calculate the water permeability in liter per second per square meter. Here I will talk a bit how we optimize the cement paste. We started or investigated 3 different mixtures, starting from mix 1, which consists only of water and cement, with a cement ratio 0.3. The second one consists of water, cement, and super plasticizer. The reason that we decided to use super plasticizer in this case was to increase a bit the amount of the cement, aiming that we gonna increase the mechanical properties. And the mix 3 consists of silica fume, super plasticizer, and cement. The aim of using super silica fume was to somehow, you know, that silica fume particles are way much more smaller than cement particles. And what we wanted is to fill the interparticle voids of the cement. Theoretically, we would have higher mechanical properties, and the sample would have a higher resistance against frost and thaws. The samples in this slide were tested after 7 days. Crushed aggregate 2 to 4 millimeter was used. In the x-axis, you can see the slurry quantity related to the mass of aggregate, and the y-axis is shown the flexural strength. I forgot to mention, by the way, according to the Austrian standard, concrete paver should have at least 3.6 megapascal flexural strength. As you can see here, there was no significant impact of the admixtures. Here I will show you some cross section of the samples. You can see here a sample made of 40% slurry content, based always in a mass of aggregate. Water permeability measured in this case was 0. You can see the blocked voids in the bottom of the samples and in the side of the samples. We have some not connected voids in the middle. Here you can see a sample made with 35% void slurry content based on the mass of the aggregate. In this case, permeability is nearly 0, but you can see the more voids in the middle of the sample. And the last one, you can clearly see the uniform distribution of the voids with 28 slurry content based on the mass of the aggregate, and the permeability in this case measured was higher than 20 liters per second per square meter. Okay, in this slide I will talk a bit the impact of the slurry quantity on the thickness of the sample. In the x-axis, you can see the cement paste quantity related again to the mass of the aggregate, which is constantly increased. In the y-axis, you can see the thickness of the sample. The way of compaction and vibration energy mixing was the same as before. The sample was compacted and vibrated for 30 seconds, and then the stone was removed. A plexiglass plate was placed above, and the thickness was precisely measured. Crushed aggregate, in this case 3 to 5, a constant mass of 2.3 kilos was used. You can see that we have an increase on the thickness of the sample between 17.1 and 30.3% cement paste, which means that the cement paste is not only located on the void content, but in the surface area covering the grains, leading to increased diameter, which would change theoretically the ability of compacted grains. Above 31.3%, we don't have any increase on the thickness. You can see a sharply drop, which means the cement paste reached the limit on the surface of the grains, and the rest is flowing into the voids on the bottom of the samples. Further analysis have shown, macrostructural analysis as well, that above 35%, permeability of the samples is 0. Here you can see the correlation between cement paste quantity and flexural strength. you can see the increase on flexure strength by increasing the cement paste quantity. And here you can see the correlation between flexural strength, void content, and cement paste quantity. The void content was determined by water displacement water method. In this test, it was found that in order to achieve sufficient water permeability, the void content should be 20 to 30%, and in order to achieve desired mechanical properties, the cement paste should be between 28 and 35%. In this slide, I will talk a bit about the impact of the aggregate size on the flexural strength. The lowest flexural strength was achieved with river aggregate 1 to 3. The highest flexural strength was achieved with crushed aggregate 3 to 5, and supposing that this is happening due to a roughness surface of the grain, which provide a better adhesion of the cement paste. And yeah, the cement paste in this case was 30% based on the mass of the aggregate. Cement paste based on the mass of the aggregate, I know, and I think you know that is not the right solution, because in river aggregate, the smaller the grains are, the surface area is smaller, and the bigger the aggregate is, the surface area. I mean, I mixed river aggregate has more surface, smaller grains, bigger grains have smaller surface, which leads to less contact points between the grades, the grains, and theoretically lower mechanical properties. Yeah. Take home message, as I said, the cement paste should be between 28 and 35% based on the mass of the aggregate. A river aggregate can be better packed than crushed aggregate due to the rounder surface. Crushed aggregate has a higher strength than mixtures with river aggregate. For all the samples that I showed in the previous slide, the water permeability was higher than 20 liters per second per square meter, and the void content should be between 20 and 30%. The water permeability mechanical properties are directly related to the compaction and vibration energy, as well as contact cement paste quantity, and needs still to optimize and study it. For my PhD, I'm working currently in 2 projects, wood cement bonded particle boards, where right now we are investigating how to extract the sugars from wood in different fresh states, and investigating their impact, the sugars on a setting time of cement. We are trying to identify some new accelerator which would help somehow the setting time of the cement, making it faster, and impact of curing temperature and time on mechanical properties. The new second project is about biochar, impact of biochar in reducing the CO2 emissions in concrete. Right now, I'm investigating the impact of the milling time in particle size distribution and mechanical properties, and I'm learning or trying to find a way to determine the porosity and density of the biochar fine particles. That was all from my side. Thank you for your attention.
Do we have questions? Mustafa. Konstantin, sorry.
Okay. Hey. Well, excellent talk. I really enjoyed, and I think excellent material, also exciting material. But my question is, in your formulation, why you didn't use sand? Because sand was let's say, this material was first time I was not reading when first paper came about, it was called no sand concrete actually.
Yes.
And I don't know if you remember Professor Swamy from UK, he was writing this article. So it was, for me, it was like my first idea. It gave me a first idea about pervious concrete. And so the sand was basically, this material was created as reducing sand and like 25% of sand from classical mix, 50% sand off from classical mix, 75%. So, but in your case, it's 0 sand. So what's
Yep.
the motivation to have pure cement paste in the system? And relatively rich, I would say, and silica fume is there as well. So I would say, what was the motivation? Because the mix which you have is rich, most probably over shrinking, and having no sand, I feel it's like a little bit alarm for me. So if you can explain.
First of all, when I started to investigate the topic, the idea was to increase as much as we can the porosity of the sample. As I said, this is just my master thesis. After I finished the master thesis, I read that kind of paper that using a tiny amount, 5% or 10% of the fine sand may increase the contact points between the cement paste and the larger grains, as well as silica fume. But in our case, as you saw, the silica fume had no significant impact on improving the mechanical properties. Right now, this topic is unfortunately not ongoing because I simply don't have time because I'm working in 2 different projects. But yeah, this may work to increase the mechanical properties, and the may increase as well the resistance against flowing during the manufacturing process.
Yes.
Okay,
I'll tell you. Yes.
Okay, so second question is actually the major issue with this material is still how it would serve in freezing condition. Obviously, for Egypt, I think it's no any like concern at all. So it's ready to go. And but all these benefits, again, I've seen this material was applied in Chicago, and we had even company in our area. They were producing actually the slabs reinforced, unfortunately, and I didn't see them much applying. So they were promoting heavily.
So you mean porous concrete, reinforced porous concrete?
Yeah, reinforced porous concrete slabs. So they were hollow core slab manufacturer, and they would extrude and produce this hollow core slabs with reinforcement, and they would market it as a sidewalk material, like you just drop the slab, not the block, but the slab. But it didn't fly for reason that, well, cleaning is one thing which is solvable, but the major problem was with the low temperature freeze thaw. Basically, in your structure, if drainage is achieved, perfect. But if bottom layer is frozen, soil is frozen, moisture is building up, you know, it's
clogging.
Way to disaster. So, do you have any solution for it, or potential solution? Do you envision how to address this?
We didn't test, unfortunately, the sample against frost and thaws. With your question, you mean during the winter they may have some blocked?
You have 100% saturated sample, like, you know, all the water, put it in a plastic bag, fill it with water. Not a lot of drainage because it may happen. Oh, take a block, put in a plastic bag, fill with water, put it in the freezing chamber. How many cycles it can resist?
I didn't test it. I cannot give you the answer, but for sure less than normal concrete.
way lower.
No, but that's a good point because the porous network that you're having is totally connected, right?
No,
It is.
It is,
is.
right? So maybe there is not much of a stress going on because as long as you can pull off you can grow, the thermodynamics is the principle of laziness. As long as you can grow this way, you don't need to push in this direction.
Yeah, but you don't have, imagine you have freezing conditions, so bottom is frozen and it is.
In the real slab, you mean, yeah, on the
It
road.
will
Yeah.
build up,
Okay, all right.
build up, and
I
this
mean,
is
Yeah,
what-
because
My-
I can tell you that, I mean, we for other reasons, if you make the surface different, the surface chemistry different, carbon cement, for instance, is resistant to freezing. Why? Not because the ice is not there. It's just the I would say, it's
There
it's
is
not,
a-
it's,
Okay.
the
this
idea is,
solution.
no, the
This is
idea,
possible
let's
solution.
mislead. The idea in civil engineering that the ice occupies 9% more
Yeah,
volume than liquid water is true. But the problem of freezing is an ion problem. It's an ionic problem. It's not a volume problem. We can discuss other things. But then that's my
Process in between the.
yes, yeah, okay. I know the beliefs in civil engineers, but then we can discuss more about physics. The thing, my question is, but what about the type of grains? Do you assess the chemistry of those? The
No.
binding with cement, for instance, is really
No.
dependent of the type of OH groups you have at the surface.
no.
Never tried, I think.
But we discussed that we have a different gradient properties. When
Okay.
in our case, the grains were completely dry,
Mhm.
which leads when in a bottom layer of the cement paste and on a top layer of the cement paste, actually the grains would absorb some water.
Yeah.
And theoretically you would have a different water to cement ratio in different layers of the cement paste.
Yes, but again, it's just like the talk this morning by it was Mohammed. Was about the interface between the palm fibers and the cement and the clay. In your case, will be the grain and the cement,
Mhm.
and the addition of those is really dependent on the state of the chemistry of the grains. Okay.
No, we didn't. Unfortunately, we didn't do anything
Okay.
about that.
Katerina, yes, we go.
Thank you very much for your talk. It was very interesting. If I understood well, you use different sizes of aggregates.
Yes.
Have you tried to see if you have a larger polydispersity? I mean, mixing
I
them
don't.
to-
I'm not hearing you well.
if you have a
Is it work?
if you have a larger polydispersity of these grains, if you mix the sizes together, could you have similar properties of water permeability with higher mechanical properties, maybe?
You mean to mix two types of grains?
Or more?
Yes,
because-
I investigated that a lot.
Mhm.
Like I tried to mix 4 and 8 millimeters with 2 to 4. The packing density, the solid volume fraction was increased. The permeability was lower.
Okay. Mhm.
As I said, you will increase the contact point between the grains and you will increase
Yeah.
but the question that I always have is it better to have larger points or voids or smaller voids, which is better. If you test the samples against clogging, I don't know. I'm not sure.
Or more important is the connectivity.
Yes.
How the pore throats, the size of the pore throats, so that
Yeah.
water can flow through. And another question: how is this influenced by the compaction and vibration step of your protocol?
In the lab.
Yes. So if you change the compaction and vibration, can you play around with the volume fraction that you obtain? Because you could play also with a little bit with the overall thickness of the sample.
You mean this slide here? Where was it?
At the very beginning, I think. Yeah. Okay.
This
Yes,
slide.
you have a different thickness there. Yeah. Mhm.
Like the compaction in our lab, that's why we use a concrete sample to have always the same compaction energy, and the vibration energy was always the same. Like depends on the grains, depends on the surface area, depends on a lot of parameters. By the way, I conducted to the company some experiments, and when we tested, the results were 30 to 40% what concern mechanical properties lower than in the lab. And this is the impact of compaction and
Of the
vibration
compaction,
energy.
Okay.
Yeah.
So it's quite a crucial step, this step,
Yeah.
right? Okay.
So maybe using some fine particles of the sand may help.
Do we have more questions?
Thank you.
Yes, please.
Can I ask one question?
Is this intended for main traffic pavement or sidewalk pavement?
Like
Oh, yes. Okay, 9. Sorry, guys.
it can be used for low traffic pavement. It can be used for sidewalks. It can be used for parking spots.
Yeah, on the sidewalks, I would understand that, but have you thought about the impact and the dynamic effect of vehicles on the
You mean
crushing?
the abrasion?
Sorry?
You mean the abrasion, like the surface, the roughness of the surface?
Yes,
So-
on, I imagine that if I have this kind of effect of impact and dynamic loading, it
Mhm.
will make kind of a crushing effect on the mix or on the pavement that will bond between the particles.
Yes, I have thought about that. There are some polymers which you can apply it in a surface, which will increase the resistance against the abrasion without blocking the voice, just the surface.
Okay, good.
Yep.
All right, we have a question online.
Can I just perhaps my connection was not very stable, so I may lost some of what you said. So forgive me if I repeat something that you have already talked about. I was wondering, because it sounds like a pretty good idea to have this possibility of a permeable pavement. Did you do any testing with respect to temperature, like heat absorption in the same material? I guess this will have to do with the grain that you're using, like materials that you use. But one of the main problems that we have in these types of pavements is, especially in Mediterranean cities, like Athens or Cairo, is the heat during the warm days and how these materials absorb the heat.
Yeah. So your question was about heat absorption of the.
Yes. If you test it in
No. I read a paper where saying that it may reduce the heat island, but we did no test about that, unfortunately.
Thank you. I believe this should be a critical question that you will have to address in the future, just because it's a huge problem. All these pavements look super nice, and the permeability aspect, I guess, is an excellent feature. But one of the problems that we face is exactly the high heat, like high temperature during the summer and the spring in urban environments. So, perhaps it's a good idea to experiment with different, materials and see where you can get with that.
To be honest, my first goal was, because when I got the topic, my first question was that I asked myself was how is possible having so much void content, like
Right.
positive.
No, it's great.
My first goal was to achieve the mechanical properties and the water permeability, and I'm quite optimistic that even in a factory can be produced. What concern frost and thaws, what concern clogging, what concern abrasion and heat island, as I said before, this whole mixed design should be still investigated and optimized.
Right. Thank you.
You're welcome.
Any more questions? So if not, thank you.
Thank you.